Now we will discuss second law of thermodynamics. The first law of thermodynamics was about energy, internal energy. It states that internal energy can be changed only by work or by exchange of heat energy. Now we will look at what this second law of thermodynamics
Sir, I
is.
can't say now. Sir, I can't see the whiteboard.
Wait. Just give it a try, like the whiteboard setting in the system.
No, sir.
Now can you see this?
I think you have to
Uh-huh.
share again.
Would I have to share it again?
Yes.
Just so let me share the whiteboard one second. So I'm sharing the whiteboard. Present. It's loading. So sorry. Different loading. 111. Once again, I'm sharing. Just a
Yes, yes. Yes, sir. Now it is visible.
yeah, now it's visible. Okay,
Yes.
okay. Nice. Now we can start. So second law of thermodynamics. So the idea is that see, we get new law when the previous law is unable to explain some phenomena. Then we need new law to explain those additional phenomena. So there were some drawbacks in the first law which led to the second law. That is what we will discuss now. So the first law of thermodynamics, it definitely it mentioned about the change, but only in terms of the quantity, but not in the direction. So first law of thermodynamics did not say anything about the direction of change. Direction. And here, when I talk about the direction of the change, I am talking about spontaneity, spontaneous process. Spontaneous change. Because we basically, when we observe the real world, the phenomena, when we look at it, we see that many of the chemical reactions, they are spontaneous in one direction. Like, just to keep it, it will automatically undergo a reaction, and it will be spontaneous. Like the sodium, when it reacts with water, it automatically reacts with water. It does not need any special condition for that reaction. So first law of thermodynamics says that, okay, if this much work is done, this much heat is supplied, then this will be the internal energy. But it is unable to explain why certain chemical reactions, they take place automatically in a particular direction, but in the reverse direction, those reactions does not take place. All that stuff, like the observations we see. And that is what is second law of thermodynamics is about. So second law of thermodynamics, the main focus is on the spontaneity. And the first law of thermodynamics, the main focus was on the energy. And in the thermodynamic system, that energy is the internal energy of the system. Now let us look at the second law of thermodynamics in some detail. Now we got the background of it. Now the second law of thermodynamics, the main point which it makes, it says that heat does not flow spontaneously from a cool body to a hotter body. Heat does not flow spontaneously. Spontaneously means on its own, naturally. Heat does not flow spontaneously from a cool body to a hotter body. And we know that heat energy always flows from high temperature to low temperature, from a hotter body to cool body, but not in the reverse direction. And second important observation, or the finding of the second law of thermodynamics is, this is very important. It talks about the entropy, because this spontaneity and entropy, they are related with each other. So the entropy, that we represent with S, of an isolated system, the entropy of an isolated system is that system in which no exchange of heat and no exchange of matter will take place. Very important, because these laws, these small things plays a very important role, because in an open system or in a closed system, this statement might not be valid, but this statement is only valid for an isolated system. So the entropy of an isolated system increases in the course of a spontaneous change. Say the whiteboard is slow. The force of the spontaneous. The force of a spontaneous. It means that whenever a spontaneous change occurs in a system, the entropy of the system will automatically increase. And this is very interesting. Spontaneous change. So one very important result we get from here, that is delta S total, like the total entropy of the system. Delta will change for a spontaneous change. If the system is undergoing any spontaneous change, then this delta S has to be positive. Because second law of thermodynamics clearly says that if there is any spontaneous change, then entropy will increase. It means that delta S will be positive and entropy is increased. And S total, here S total has a meaning. The meaning is that S total means uh, total entropy. It means the entropy of the system plus entropy of the surrounding. S total is the entropy of the system plus entropy of the surrounding. Entropy of the system plus entropy of the surrounding. Okay. This is very clear. So this is the second law of thermodynamics, the mathematical aspect. And very important observation we have to make. Here we are talking about the total entropy, not the entropy of the system. So the second law of thermodynamics clearly says that in a system, in an isolated system, if any spontaneous change is taking place, then the total entropy of the entire system, or not entire system, but the total entropy itself, including the system and the surrounding, will increase. There will be a positive change. The total entropy will increase. And we can understand it from a different context, from our intuition. We can understand it. See, entropy is also the randomness in the system. We say that okay, if a system is having lots of gas particles, so they are randomly distributed, we say that okay, very high entropy we have. So whenever any spontaneous change takes place, whenever any natural chemical reaction is taking place or a natural process is taking place, then ultimately energy exchange will take place. New bonds will be formed, new compounds will be formed, and it will lead to some kind of a liberation. We call it like the solid metal, if it is getting converted into gaseous particles, some kind of a liberation is taking place. And that liberation is what is resulting in the increase in the total entropy of the universe, because it is S total. So first law of thermodynamics talks about the internal energy, and the second law of thermodynamics talks about the entropy. Now we can state this, like the third statement we can make from the second law of thermodynamics, and it's a very important statement we are making. A spontaneous process a spontaneous process So if we are having a spontaneous process, it will always point towards the direction in which the total entropy increases. A spontaneous process points
So what does this mean?
yeah, yeah. It will make sense very soon. I will explain. A spontaneous process points towards the direction in which direction total entropy increases. That's right. So it means that see, let us suppose I have a process. I have a process which can go from A to B. I, I have A, I have now this A can be a solid state and B can be the gaseous state. So let A be the solid state, like any solid object I have. B let it be the gaseous form of that solid. And burning, I can say it to be a spontaneous process because I just have to initiate that process. Like I have the wood, I just have to initiate the fire and just I
Yes, sir.
have to initiate the fire. So the burning process will start. Now the idea is that burning will happen automatically, spontaneously. Why? Because in this direction from A to B, the entropy is increasing. Because the solid particles, they are getting converted into gaseous particles. So they are liberating themselves. The total entropy is increasing. So the idea is that only those chemical reactions will take place in which the entropy is increasing. And hence we see so many chemical reactions don't take place. Like if you take any two random compounds, you mix them, add some water, add some acid, and you see nothing is happening. Sometimes we see nothing is happening. It means that
Mhm.
the reaction which we are trying to carry out, that is not taking place because the direction in which we are trying to initiate the reaction, in that direction, total entropy is not increasing. In short, I can say that all the chemical reactions which is taking place, all the chemical reactions which is taking place in the direction of the chemical reaction, total entropy is increasing. Delta is total is positive always. So any chemical reaction you take, just write this second law of thermodynamics. Okay, if chemical reaction is taking place, it means that in the direction of the chemical reaction, delta S total is greater than zero. That is the second law of thermodynamics.
Mm.
Now this entropy which we discuss, so this entropy is a state function because this like temperature, pressure, enthalpy. So, I know this thermodynamic parameters we discussed. So many thermodynamics parameters we already discussed: volume, pressure, temperature, enthalpy, internal energy. Similarly, entropy is also a thermodynamic parameter. We can say, and this entropy, it is a state function. It means that it does not depend on the path. We have a path
Yes.
function. We have a state function. It's a state function. Like pressure, volume, they are the state functions. I can write it. Entropy, which we can represent with a capital S, is a state function. Entropy is a state. Now we will get some more clarity about entropy. Now we will get some more clarity about it. I can write thermodynamic definition of entropy. Like from the thermodynamics perspective, what exactly is entropy? Because until now, we haven't formally defined the entropy. We just have
Yes.
been focusing on the second law of thermodynamics.
Mm.
So, properly. Or, you know, definition of thermodynamic definition of let us do this. Now the change in entropy, like from experimental perspective, if we try to understand the entropy, like we have been discussing about the delta S change in entropy.
Mm.
So this change in entropy can be carried out either via any physical process or a chemical process. Either via any physical process or chemical. Okay. This delta S we can get either via any physical process or change in entropy. Now let us suppose I have a term that is dq. dq is the change in heat energy, and rev is the reversible process. So in a reversible process, if it is not adiabatic, then definitely uh, heat transfer can take place. So if in a reversible process, heat transfer is taking place, so there will be a dq term which will be involved. Amount of heat transfer, either from the system to the surrounding or from the surrounding to the system. So that is the dq rev, heat transfer in a reversible process.
Hmm.
At any temperature T, at any absolute temperature T. So then I can say that I can now relate, or mathematically I can define the change in entropy. Because if a reversible process is taking place, then entropy will change. Any process is taking place, any spontaneous process is taking place, entropy has to change. So ds will be dqrev upon capital. Delta S is equal to integration initial to final d u rev upon capital. So this is the thermodynamic definition of entropy. So change in entropy can be done by a physical process or chemical process, because any process, spontaneous process is taking place, entropy has to change. And mathematically, what will be the change in entropy? It will be the integration from initial to final, the heat transfer upon time, upon temperature, absolute temperature, at which that process is taking place. So the heat transfer involved in that process upon the absolute temperature, the integration we will do, we will get the change in entropy. Now let us look at some processes for which delta S is greater than 0. Because only those processes are spontaneous. No? For spontaneous process, delta S has to be 0, greater than 0. That is what we are discussing.
Yes, sir.
Process that leads to an increase in entropy. Process that leads to an increase in entropy. Process for which delta S is greater than 0. It's very easy to understand. Whenever we go from solid to liquid, entropy will increase. In this process of like melting or whenever we are going from solid to liquid, entropy is increasing, and hence it's a spontaneous process. Like under suitable condition, it will occur. Liquid to vapor. It's a spontaneous process. I have a solute, like in the solution, I have a solute that can get dissolved in a solvent. And if I do that, I will form a solution. So when the solute, it gets dissolved in a solvent to form a solution, entropy will increase. And hence it is a spontaneous process. And it's so interesting example, like sugar in water, spontaneously it dissolves. It forms a
Hmm.
solution. But not all uh, compounds is soluble in water. So their entropy is not increasing, and hence the process is not taking place. The dissolution process is not taking place. And the idea is that these processes, if we look at, you can see that as we go down, the disorder is increasing. Increasing disorder. And hence entropy is increasing. Why is it so? Because in liquid, the particles are relatively packed, but in vapor, too, they are free to move. High disorder. And in solution, since it's a combination of particles, in vapor, too, we can say that okay, it is only made up of one type of a gaseous atoms. But in solution, though, we have solvent atoms, we have solute atoms, and all that. So high disorder is in solution. The disorder is way high as that of the vapor, and hence entropy is increasing down the order. So this is also clear. Now we will be discussing entropy for an isothermal expansion of a perfect gas. The change in entropy for an isothermal expansion of a perfect gas. Entropy change for the system of isothermal expansion of a perfect gas. Now see, isothermal means neither the matter is exchanging or nor the okay, sorry, that is isolate. Isothermal means constant temperature, and when the temperature is constant, when the temperature is not changing, internal energy will not change. Very important discussion I am making. Whenever the temperature is constant, internal energy has to be constant. So in an isothermal process, delta U has to be zero. No change in internal energy will be. Since expansion is there, the work done will be like by the system. So work done can be negative, but yeah, we can prove that. How we can prove that from the first law of thermodynamics. So first law of thermodynamics says that delta U is equal to Q plus W. Since delta U is zero, I can write 0 is equals to Q plus W, or I can write Q is equal to minus W. In an isothermal process, this condition holds. And this will hold for reversible process also. Because in reverse nothing new will happen. Because if the condition is isothermal, regardless of it is reversible, irreversible, temperature will be constant, delta U will be zero. And if delta U is zero, this equation will hold. And I can write it Q ReV is equal to minus WR. This is clear. And here ideal gas is involved. And for ideal gas, we already know the work done that I can write it. We have proved it earlier. So reversible work done for the isothermal expansion of a perfect gas, it is minus nRT log Vf by Vl. This we know the formula. And if we use it, and why negative sign? Because the work is done by the system. The work is done by the gas. I will get a new relation, that is Q RE. Like the heat involved in that reversible process, that will be nRT log Vf upon Vf. Now we already know one more formula, the formula of the entropy, change in entropy, which we just now discussed in terms of heat and the temperature. That formula is ds is equals to dq rev upon capital D is the temperature, and using that I can write delta S will be equal to nr, tt will cancel, nr log Vf. So this is the change in entropy for an isothermal expansion of an ideal gas. Let me like that. This is now we will look at the next concept, that is the total entropy change in irreversible process. Now it was a next we will discuss. Total entropy change in irreversible process. Total entropy change in irreversible spontaneous process. Of a perfect. So whenever we are talking about irreversible process, free expansion is a very good example. And we
Hmm.
have already seen that in some about context when we were discussing first law of thermodynamics. Free expansion. And we can achieve free expansion in like this also. Isothermal expansion of an ideal gas. Isothermal expansion of ideal gas at constant temperature in vacuum. Isothermal, it has understood temperature is constant in vacuum. So whenever I talk about free expansion, I'm talking about vacuum. Because there should not be any external pressure. Then only I will be able to achieve the free expansion. So whenever I'm talking about the free expansion, I'm talking about the vacuum, and here I'm talking about the isothermal expansion of an ideal gas in vacuum. In that scenario, basics I know, work done will be zero, no external pressure, no force need to be applied, work done will be zero. Since it's an isothermal expansion, delta U will be zero, temperature is constant, no change in internal energy will take place. And from first law of thermodynamics, If both the terms are 0, then Q has to be 0. Q has to be. And if Q is 0, or to be more precise, it should be delta Q is 0. So what it means? It means that no heat transfer. So in this process, in the process of isothermal expansion of an ideal gas in vacuum, no heat transfer will take place, according to the first law of thermodynamics. Okay, it's fine. And we also know that from second law of thermodynamics, delta is related to Q by capital T. Since Q is 0, delta S has to be 0. Okay. Now here, one very interesting thing we are doing. See, here this Q is equal to 0. We are assuming that since there is no heat transfer taking place, so the surrounding will neither intake any heat nor lose any heat. So we will say that delta S of the surrounding, delta S of the surrounding is 0. Okay. Yeah. Delta S of the surrounding is 0. Delta S of system, why we can't take 0? Because system is not vacuum. System has gas. And if it has gas, entropy has to be there now. And if expansion is taking place, because the system, from the reference frame of the system, we can see that oh, we are expanding, the gas is expanding. And if the gas is expanding, entropy has to increase. Entropy has to increase. Delta is it is 0 because surrounding is vacuum also, and we can say that no heat transfer is taking place. So using this, we can write one very interesting observation. And delta is n. M means system. So change in entropy of the system will be the that formula which right, that is Q by T. So T will cancel. So R log Vf by Vi. And we are taking 1 mole of gas. So instead of n, I can write 1. So this is the change in entropy of the system. Now the total I can calculate. Total I can. S total will be, or I can write delta S total. Delta S total will be delta Sm plus delta S surrounding. And I can substitute the value and calculate the total change in entropy. It will be R log Df upon Q. Since expansion is taking place, so Vf has to be greater than Vi. It implies that delta S total is positive. Because if Vi, if Vf is greater than Vi, delta S has to be positive. And if it is so, then what I can say? Then I can say that the process is spontaneous. This isothermal expansion of an ideal gas in vacuum, it is spontaneous. Spontaneous, irreversible. Isothermal expansion of ideal gas. So the main crux of this discussion is that in the free vacuum, in the free space in the vacuum, if we take a system containing an ideal gas and keeping the temperature constant, if we just don't do anything, we will see that spontaneously on its own, automatically, the ideal gas will start expanding. That is what is spontaneous is. And why it is doing so, mathematically we have proven that. Because in that direction, in the direction of the expansion, the entropy is increasing, and hence it's a natural process. But in the opposite direction, it will not work. The opposite direction, entropy will not increase, and hence it is irreversible. Once the gas got expanded on its own, it will not contract. We have to apply external force for the contraction. On its own, it will not contract. Now we will discuss one more concept here. That is a isothermal reversible expansion. This is very interesting that here the expansion can take place in both the direction. Reversible. Isothermal reversible. So since it is isothermal, delta U will be 0 and work done will be by the system. It will be negative. And P into delta. And the heat energy will be according to the first law of thermodynamics. Since delta U is 0, U plus W, delta U is 0. So 0 is equal to Q plus W because it's isothermal. So Q will be minus W. So Q will become minus minus plus P into delta V. Whenever we are talking about entropy, just calculate the Q. And Q by T will give us the change in entropy. Now we can calculate delta S total. Delta S total is the delta Sn, that is the delta S of the system, plus delta S surrounding. Delta S surrounding. Now, since it's a reversible expansion, in both the direction, we can do an equal amount of work. So the work done by the system, like when the work is done by the system, delta S is Q by capital T. So the Q is P delta V. I can write P delta V upon capital T. Or I can write Q RE, which is P delta V upon capital. And since the temperature will be same at that point, so for the surround, see, whatever heat transfer is taking place from the system to the surrounding, it's a reversible process. In the opposite direction, the heat transfer will take place from surrounding to system. This property is followed in a reversible processes. And hence, delta S will be 0. Because in the lab, we can achieve isothermal reversible expansion. It's very possible. And now this, and it is not a spontaneous. And we know that reversible expansion cannot be spontaneous. In the one direction, it can be spontaneous. In the one direction also, it will not be spontaneous because there is an external pressure acting. In order to achieve that expansion, I have to do some work. And if it is reversible, if the work can be done in both the direction, it cannot be spontaneous. Spontaneous means it will work on its own. Like in the vacuum. In the vacuum, you don't have to do anything. Just place the system. That's it. Automatically it will expand. Like the plants, just the seed, you sow it the soil, and just it needs water. Just give it water, and you have to do nothing. It grows. So that is the spontaneity on its own. Now, one more concept we can discuss. So we are discussing the second law of thermodynamics. We can discuss relation. One inequality we will discuss. Clausius. Inequality. This inequality states that change in entropy is greater than or equal to dq by t. Because the formula of change in entropy is dq by t. So delta S can be either equal to or greater. Now what it is, let us try to see. See, basically in isolated system, in isolated system, there will be no heat transfer. If there is no heat transfer, then delta S will be zero. That is understood. That is understood. Because the formula of delta S is delta Q by T in isolated system. The definition of isolated system is that no heat transfer, no matter exchange. So delta S will be zero. Or delta S can be greater than zero also. Because in isolated systems also there are spontaneous processes possible. It implies that delta S can be greater than or equal to zero in isolated systems. From this, we can say that all natural processes which we see around us, naturally occurring processes, all natural processes are spontaneous and irreversible. And this is a very interesting observation we have to make. Irreversible. If the plant is growing, it cannot degrow. It will keep on growing only. It cannot degrow. Like degrow in the sense that opposite direction. It is not possible. So all natural processes are spontaneous and irreversible. Now the second scenario, if I talk about reversible process, there are some reversible process also which do occur or we can make them occur. In the reversible process, the change in entropy of the total change in entropy is equal to D system plus D surrounding, like D delta, and it is zero. That we just now proved in the previous one example, like scenario that is somewhere below. To the reversible process, uh, change in entropy is zero. It means that I can say that very important point I am making. Reversible processes are not spontaneous. Like they will not undergo on its own. We have to make them undergo. Reversible processes are not spontaneous in either direction. It means that reversible process, they are always at equilibrium. Very important. It says they are not spontaneous in either direction. They will not take any particular direction. They will keep on oscillating. And that is what is equilibrium.
Yes.
Yeah. The reversible processes are at equilibrium. Now we will look at irreversible process. Irreversible process. Irreversible process, we already saw some examples. It can be spontaneous. In irreversible process, we can have the entropy, the total entropy greater than zero. That is possible. Total entropy can be greater than D system plus D surrounding. DSM means D system plus DSM. It is greater than. It means that all spontaneous process, all the spontaneous process which we are seeing, all spontaneous process occurring in nature are irreversible. Very important. And that is what we see. There is nothing called degrowth. There is only growth. Like the plant, they cannot get back to the initial state. We cannot make a tree get back into the seed. It's not possible. Once we grow up, we cannot reverse our age. It would be so good if we could reverse our age. Then we could have lived here for thousands of years. So, because the growth is also a spontaneous process, automatically we are growing. Naturally, we are growing. So, all spontaneous process which we see are irreversible, and hence this entropy of the universe, because delta S is positive, it means entropy is increasing. And these spontaneous processes, they are making the entropy of the universe to increase. And entropy of the universe is increasing. Continuously. This is the idea about like the main crux of second law. So whatever we have discussed now in the name of this inequality, this is the crux of the second law of thermodynamics. This clearly states that based on the entropy, change in entropy, we can tell the direction. We saw that in reversible process, they are not spontaneous. Hence, they keep on oscillating and they are at equilibrium.
Yes.
Yeah.
Yes.
So, two more discussion we can make very quickly. Then we are going to just two more discussions. Like one very important point we are raising. So there was a German scientist, physicist. But the thermodynamics we study in physics also. So there was a German physicist called Rudolf. Rudolf Clausius. He uh, gave two very important statements. Very important statements. The first law, like he summarized the first law and second law into one statement. So the first law, it says that in very simple terms, it says that the energy of the universe remains constant.
Mm. Yes.
Energy of the universe remains constant. Yeah. And we have second law, which states that the entropy of the universe entropy of the universe tends towards a maximum. It is increasing, increasing, increasing. If it is because all the spontaneous process, they are leading to the increase in entropy. The entropy of the universe tends towards maximum. So the idea is that the particles, they are liberating from the bondage of the bond. They are becoming free. So all the spontaneous process there, and they are bonding also. It's not that, but in total, from a macroscopic context, the entropy of the universe is increasing. So this was the statement by the German physicist Rudolf Clausius.